So good morning, everyone. My name is Satoshi Ejima from the University of Greifswald, Germany. So first of all, I would like to thank the organizers for giving me this opportunity to present our recent work, photo-induced interfering in pumped mode insulators. These are the references, and main data in this talk can be found in third paper. So yesterday and today also, we had a talk about photo-induced superconducting states of the K3C60. And in order to see such non-equilibrium dynamics, we used time-dependent ED or DMFT so far. In this talk, I would like to demonstrate that non-equilibrium dynamics can be found also can be simulated by the time-dependent DMRG using the translational invariance. And we applied this technique to the optically excited motor insulator and show time-dependent photoemission and dynamic structure factor. Let me first explain our numerical technique. As well known now, ground states in the quasi one-dimensional systems can be simulated directly in the thermodynamic limit with high accuracy thanks to ITBD or IDMRG. And now, spectral functions. In order to simulate spectral functions, we need dynamical correlation functions. It is also well known now how to simulate these dynamical correlation functions. We prepare first unit cell, IMPS unit cell, using the IDMRG, and we build a so-called window sites, LW sites, and carry out the time evolution applying operator and so on. In this way, we can simulate spectral functions in equilibrium at 0 and finite temperatures with high accuracy. Our target is non-equilibrium states. So we need to consider such spectral functions, ik omega t. And here, f is f includes the Gauss functions, and c is the most important two-point correlation functions at times tau1 and tau2, which are relative to time t, and operators oj. And so our task is to prepare oj tau t times wave function phi t, which is given by u dagger o u, and u is defined as right equation. And for this, we need two processes before building window sites. Again, we prepare ground states and carry out time evolution up to time t, target time t. And then we build LW window sites, again by copying the unit cells, which is obtained by IDMRG and ITBD. And in this process, we need also so-called uniform update, which is explained in this paper by Zauna et al. And in order to update the unit cell. For further details, please see the paper by Zauna and our recent paper. Now we apply this technique to the photo-induced eta-pairing states. So our target Hamiltonian is a simple Hubbard model, and And the question might be, what is eta pairing? Eta pairing is suggested by Chen Yan in 1989, and which possesses a pair density wave like off-diagonal long-range order, and constructs the exact eigenstates of the Hamiltonian. Let me show some important stuff for this eta pairing states. And first 3 lines are showing eta pairing operators, which are given by annihilation and creation operators and number operators of fermions. And this satisfies anti-commutation relations, which indicates SU2 symmetry. And then these operators construct the eigenstate of the Hubbard model, like in middle. So, I don't know. Most importantly, superconductor pair correlation functions can be also described by these eta pairing states when the momentum q is pi. But until now, until recently, it was only specific interest, especially from the mathematical point of view, because this state, in the ground state, there exists no eta pairing. But very recently, it was shown that there exists eta pairing after pulse irradiation. And so now we consider the Hubbard model with pump pulse using Pierce phase, and vector potential is defined as follows: amplitude A0 and frequency omega p centered at time t0. In this way, Hamiltonian becomes time dependent, and we need to simulate a time dependent Schrödinger equation. And Kaneko et al. Shown that by calculating superconducting like pair correlation, significant enhancement of PJT can be observed after the pulse irradiation. And this is an example of from his paper. And after t larger than t0, we see the enhancement of these correlation functions. However, these correlation functions, or the enhancement, depends strongly on the form of pulse, and especially A0, amplitude A0, and frequency omega p. And so we calculate P Fourier transform of PRT, and especially Q is pi again. And this is a result from ED with 14 sites and periodic boundary conditions. And we can see the enhancement around omega p is U. Now U is 8. But there is a strong finite size effect as stripe structures. This finite size effect can be eliminated by simulating ITBD directly in the thermodynamic limit. And in the following, I show the non-equilibrium dynamics for first not optimized parameter, pump parameter, and optimized parameters. This is the result for not optimized parameter sets. And as you can see, almost nothing happened. And so integrated A omega t, you can see small spectral weights for above Fermi energy, but this disappears after pulse irradiation. And now for the optimized parameter set, pump parameters, we can see the extra dispersion during pump, and this persists afterwards. And this can be also checked by integrated density of states. And finally, I show also the dynamic structure factor. And at T is 5, spin dynamic structure factor shows the gap closing at momentum Q is 0 and pi, as in the equilibrium, and spectral weight is reduced, reflecting the suppression of anti-ferromagnetic correlations. And lower panels are for charge dynamic structure factor, and at T is 5, we see the gap closing, and after pulse irradiation, we have extra bands again, and concentrates, spectral weight concentrates around Q is 0.55 and omega is 0. And this might be indication of superfluidity of the eta pairing states. So let me summarize. I have demonstrated that non-equilibrium dynamics can be calculated by TD with infinite boundary conditions, and tuning the pump pulse to maximize eta pairing. We found clear evidence for photo-induced insulator to metal transitions. And since this method is very general, we can apply any quasi-one-dimensional systems with translational invariance. And we have also applied this technique to extended Farikov-Kimball model. Thank you for your attention.
Questions or comment?
Hi, thank you for this very nice talk. I wanted to ask, so you're showing at some point the spin structure factor.
Yes.
I remember in the original paper by so there is a paper by Cho-Chang about the fingerprints of the eta pairing, where it says that the staggered correlations will give you a peak at pi, an emergent peak at pi momentum. So here instead I see that there is a suppression or a broadening of the structure factor.
Yeah.
How do you reconcile that? Do you expect a peak in the pairing susceptibility?
Oh, so I don't know about that. So I have to read the paper. So sorry.
One more question.
Just a quick comment. Thanks for a nice talk. So you started with K3C60 as a motivation, right?
Yeah.
So I think in 2020 we published some paper on rapid communication working on the two-particle spectral function, not the single G lesser you have shown, not the two-particle. This has much more insight to distinguish between preform pairs and real pairs, for example. So since you have now some advantage for determining a limit, I think it's good that you maybe can combine these ideas somehow to go further and really address your motivation finally with it.
Thank you for comment.
Thank you. So I'm afraid we are behind the schedule because of my bad chairing, so we have to move on.